Hello, this is Organic Chemistry 1020 Elucidation problem solving process. This is basically our video project, and the the question I was assigned to was explanation B. And upon first glance, we're looking at ethyl propionate. When we draw out the skeletal structure, we can see that the functional group is going to be an ester, obviously. So we calculate the molecular weight based on our formula here, and we come up with 102.13 grams per mole. And then we go into our spectral problems. So we're going to start with IR spectroscopy. I'm never good at saying that word. And off the bat, we can see that we have two peaks, right? Our indicators, indicators here, we have 3,000 to 3,100 centimeters. So we have one there, and it looks like there's two peaks there. And then we go to our next main peak. This looks like just a singlet. Given that this is IR spectroscopy, that's not applicable here. But one peak, that's our largest peak, and that's going to be 1720 centimeters. That's very indicative of the carbon double bond oxygen stretch. And in conjunction with that, the 3,000, 3,100 centimeter is indicative of a sp3 hybridized carbon, which is going to be a carbon-hydrogen stretch. So sorry. So we basically go down to our 13 CNMH. Oh, a little bit of technical difficulties. I couldn't get my camera to work, so we're working with this. There we go. Okay, so we're looking here. We have, and we'll see on the next page that we have our tables filled out. This is our IR spectroscopy, and then we're now looking at the 13 CNMH. We start with our methyl group at 20. Our CH group, that'll be at 37. Our OCH3 group at 55, and our C double bond O group at 180. And all of those are indicative of certain numbers. The bonding environment correlates to certain numbers. So as you can see, 20, 37, 55, 180. And that's how we find those based on the specific functional groups within the compound. Something to add is when we do these things, we have to find the degree of unsaturation. So in order to do that, we plug in our formula. We see our carbons. We have 5 carbons because we go back up to the formula here. We see that we have 5 carbons, 10 hydrogens, 0 nitrogen. Plug in, and the 1 will imply that we only have 1 double bond present within our compound. Lastly, we're going to go to our 1H spectroscopy, and this is where we're going to have the singlet, pentet, doublet. All right. So our integrations, we have our 6H, so we have our two peaks with our doublet. That's at 1.1. And then here at 2.7, we have our 1H. That's our pentet because we have 5 peaks here. Hard to see because I highlighted it, but it's there. And then our last one, 3.7, we have 1 peak, our singlet, and that'll be our 3H. Something important to note for our doublet, that's indicative that the protons lie far away from the electronegative group. So that's right here at 1.1. When we're at our pentet here, the protons lie close to the group, so we know we're within range. And lastly, for our singlet, the protons are going to be very close to the electronegative group. Not as close as our pentate, though. Okay, so we go here. This is going to be our proposed structure. The IUPAC name is polyactic acid. And as you can see, we've assigned our doublet to our methyl groups. Our pentant is here, adjacent to our double bond oxygen. Our singlet is at the end of our methyl group, basically at our 1, 2, 3, 4, 5, our 5th carbon. And basically what we determine from all of this is that protons lying closer to the electronegative group will have more of a chemical shift. So these are faced with the most chemical shifts. And that is our explanation B for our final video projects.